All right, same thing as last time. Ask questions. As soon as you stop asking, I leave. Who's first? Yep, Janae.
Five on summer 2019.
Summer 2019. Number 25, you say. All right, probably would help if I actually connected the monitor so that you guys could see it and not just me. Oh, there we go. Thinking about it, or it was. My screen's doing that weird thing where so let me connect to it wirelessly. Sorry about that. So for number 25, we want the, oh, okay. No, it's not the one that I thought it was. Okay. So this is very similar to homework 12, problem 3, if I'm not mistaken, which I believe I also explicitly warned you guys about, as saying that I liked that problem as well as homework 12, problem 5 as potential test questions. So in this one, we're told that our source current has some value. The voltage drop across our source is 26 volts at T is equal to 0, and we're trying to find the capacitor voltage at T is equal to 0. So we have the following relationships. We know that current flowing through a capacitor is equal to C times the derivative of the voltage drop across the capacitor, or the voltage drop across our capacitor is equal to 1 over C times the integral from some point in time T naught where the voltage drop across the capacitor is known to some later point in time of IC T prime dt prime. So those are our capacitor relationships. We're also going to wind up having to look at our inductor relationships as well. So I'm going to tack them on over here. The voltage drop across an inductor is L di by dt. And the current flowing through an inductor, which we're not actually going to have to use this relationship, is 1 over L times the integral from T naught to T. Oops, actually, I made a small mistake here. Plus VC at T naught. VL of T prime, dt prime, plus IL at T naught. All right, so the reason why I wrote all those out is because we're going to have to wind up using this guy and this guy in our Kirchhoff's voltage law equation, right? So, by inspection, we can say that Vs of t is equal to the voltage drop across my resistor, where I'm assuming positive polarity on the left, plus the voltage drop across my capacitor, plus the voltage drop across my inductor. We have an expression for Vc of t. We have an expression for VL of t. So the only thing that we're really missing, I'll tack that down here, would be VR of t is just going to be R times IS of t. Right? Just good old Ohm's law. So value of the voltage Vc at t is equal to 0. All right, so let's come down here. Let me rearrange this slightly. Since we're trying to find Vc at 0, this will be equal to Vs at 0 minus VR at 0 minus VL at 0. Everybody okay with that? So I've just reorganized my Kirchhoff's voltage law expression, and I'm explicitly evaluating it at t is equal to 0 because that's what we're interested in. Okay. So Vs at 0 is very obviously, actually, 26 volts. We were already told that. Let's see. So VR at 0 is going to be 5.1 kilo ohms times 18 milliamps. Whatever that comes out to be. And do it down here. VL at 0 is going to be 25 millihenries times the derivative of this thing. So that's going to look like 18 milliamps, negative 25,000 per second, e to the negative 25,000 t evaluated at t is equal to 0, which effectively just means this whole thing right here is just going to look like 1. Right? So I have VL at 0, I have VR at 0, VS at 0 was given to me. Now I solve for VC and I'm done. Next. Patrick. Fall 2020, number 24. Fall 2020, number 24. Oops, that's the wrong thing. You said 24, right? Which problem again, Patrick? My memory is that of a goldfish. All right, while he's getting stuff sorted out, somebody else asked. Number 24. So time constant. Okay. All right. Yep. So for this particular problem, the switch is closed at position B during the transient condition. Okay. So here are the terminals of my capacitor. Because I'm finding an equivalent resistance, I need to be looking at a dead network, so that voltage source gets turned off. Here is a 4 ohm resistor. Here's terminal A that's open circuited. Here's my 8 ohm resistor. My switch is closed up here at position B. And then my current source is going to look like an open circuit. So I see 12 ohms.
So.
Because we're looking in. The capacitor does not become, hold on, screen scrolled on me. The capacitor does in no way, shape, or form become a short circuit. We are finding the Thevenin equivalent resistance with respect to a particular circuit element. It is the energy storage element. So that gets taken out. It is an open circuit.
And that applies for inductors as well.
Yes, we're taking it out of the network and looking in through the terminals left behind. Because all we are doing is finding the Thevenin equivalent resistance with respect to the energy storage element in our system. Yes. So when we're determining REQ for these transient analysis problems, we take, it doesn't matter if it's the inductor or the capacitor, replace it with an open circuit and look in through those terminals. Okay. What's next? Somebody else. So for number 25, I'm assuming you're willing to accept the previous part's answers, because this is the, yep. So let me look at this thing really quickly. So I think this is a total response problem. It definitely is, because the 7-volt source and the 3 amp source are both connected at t is equal to infinity. So for number 25, we're going to have IR of t will be equal to IR at 0 plus minus IR at infinity e to the negative t over tau plus IR at infinity. Let's substitute things in here. So IR at 0 plus looks to be 1 amp. IR at infinity is 3 amps. E to the negative t divided by 1.5 milliseconds. So 0.0015 seconds plus 3 amps. And then t is equal to 4 milliseconds. So we're going to have IR at 4 milliseconds will be equal to -2 e to the negative 4 over 1.5 plus 3 is equal to a number, which I presume is that. Yep. Yes, Bilby. Absolutely. So for this circuit here, all right, so this is effectively the exact same thing as homework set 12, problem 5. We are trying to find the inductor current at some particular point in time. All right, so let's go up here. So we have all those relationships that I wrote earlier. We can see that IS of t is equal to IC of t plus IL of t, which means that IL of t is equal to IS minus IC. We'll probably wind up using that here in a moment. We have a voltage drop, so let's see here. We'll also have IL is equal to 1 over L times the integral from T naught to T of, in this case, it'll be VS plus IL at T naught. So let's work on this part first, right? And not really giving myself a whole hell of a lot of room, but I'll sneak it in here. All right, so L is 23 millifarads. So that's going to be 23 times 10 to the minus 3. A farad is a volt second per amp. Actually, nope, I'm doing this totally wrong. I'm using the capacitor value instead of the inductor value. 47 times 10 to the minus 3 Henry is a volt second per amp. Sorry about that. My voltage, 68 millivolts, that part can come out. And then I'm going to have the integral of e to the 52t, right? Which is going to pull out a factor of 1 over negative 52 per second. And then I'm going to have e to the negative 52t minus 1 plus IL at T naught, which we don't know, right? So if we look at the units part of this thing here, this volt cancels this volt. I have seconds and per seconds in my denominator, so those cancel each other out. So the only unit that I have is amps on top, so all of that works okay. So then this begs the question, how do I find IL at T naught? Well, that's where this guy right here comes in, right? We are told specifically that IS at 0 is 32 milliamps, so now we just need to figure out IC at 0. IC at 0, let's do it over here, is going to be 23 times 10 to the minus 3 amp seconds per volt times 68 times 10 to the minus 3 volts. And then this is also being multiplied here. Negative 52 per second. And then the e to the negative 52t evaluated at 0 is just going to look like 1. So if we look at the units for this part right here, these per seconds cancel these seconds, this volts cancels these volts. And so now we have IC at 0 measured in amps. And we have all of the parts to plug into our relationship. I cannot emphasize enough that I stopped being a jackass and started actually giving you guys enough space, in my opinion, to actually work the problems on the same page as the circuit diagram and not just, here's 3 lines of space, have fun writing all over the border. Anyway, let's kill some trees. All right, are you ready now? Which test are you talking? Fall 2020, problem 11 and 12. Yes, and the capacitor is an open circuit because this is a DC circuit. And in a DC circuit, an inductor behaves like a short circuit and a capacitor behaves like an open circuit. Does the voltage or currents from the sources vary in time? No, it's a DC circuit. If they do, it's not a DC circuit. It is that simple. Is 24 volts constant? Is 9 volts constant? Is 3 amps constant? This is a DC circuit. All right, next. Brandon. Winter 2019, number 20. I guess I get asked about this one fairly often. All right, so we want the voltage drop across the capacitor at T is equal to 4 milliseconds. We are told very specifically here that we are given the current, and just to remind you guys of the relationship, VC is equal to 1 over C times the integral from T naught to T of IC T prime dt prime plus VC at T naught. So we are told that VC at T naught is 6 volts. Then we have that 1 over C bit, so this is our C. So we just need the area from 0 to 4 milliseconds. So this area right here is 1/2 times 2 milliseconds times 4 amps. This area right here is 1/2 times 1 millisecond times -2 amps. This area right here is just a rectangle, so that's going to be 1 millisecond times 2 amps. And then I have this triangle guy right here. So that's going to be 1/2, 1 millisecond, and the change there looks to be 1/2 a milliamp. Add those areas up, multiply it by 1 over C, add 6 volts, donezo. Yes. Oh, it shouldn't be. It should be amps. That's just me being dumb. Thank you for that, Faith. Yes. $29. All right, so finding the time constant for this guy up here. All right, so during the transient condition, our switch is closed at position B, which means these guys right here don't do anything. Like they're not going to contribute at all, so that's why I've X'd them out. So here are the terminals of my inductor. Here's my 10 ohm resistor. Keep accidentally erasing things and it's pissing me off. And then my 8-volt source looks like a short circuit because we're looking for equivalent resistance. So we're always looking at a dead network. And so it looks like 10 and 3 in parallel because it's 10 and 3 in parallel of the inductor. Yep. Yeah, so take the inductor out, look in through the inductor's terminals at the dead network, which means our voltage source here looks like a short circuit, which is why the 3 looks like it's in parallel. So let's draw it. How does it contribute? Terminal A is open circuited. The 3 amp current source looks like an open circuit, so it's literally just a 5 ohm resistor that's dangling there that isn't connected to anything on one side. So it can't contribute because it's not part of a closed path. Build it. All right, so Thevenin voltage, positive polarity on top for this guy. So the first thing that I would do is observe that there's no voltage drop across the 6-volt source. So this is all, or excuse me, the 6-ohm resistor. So this voltage across this current source is also the Thevenin voltage, right? So using nodal analysis, let's call this V1, V2, and V3. Let's see, so we have a voltage relationship that V1 is equal to 19 volts. Yeah, I did label the bottom as ground. We have a controlling variable relationship that Ix is equal to V1 minus V2 over 9. And then we don't write a KCL equation for node 1. We will write one for node 2. So that's going to look like V2 minus V1 over 9 plus V2 over 1 plus V2 minus V3 over 4 is equal to 0. Now we write a KCL equation at node 3. So that's going to look like V3 minus V2 over 4 plus V3 minus V. Oh shit, why did it scroll on me? That jumped like pages. V3 minus V1 over 20 minus 2Ix is equal to 0. And then we solve this system and V3 is exactly the same as VTH. So that's our Thevenin voltage. Number 14 is the Norton current. So you know what? I should have left that alone because I'm going to wind up using nodal analysis here because there are too many meshes. So let's put this back at V1, V2, and V3, right? This is our current I Norton. So everything is going to be exactly the same except for our KCL at node 3, right? So KCL at 3 is going to change. That's going to be V3 minus V2 over 4 plus V3 minus V1 over 20 minus 2Ix plus V3 over 6 is equal to 0. And then our Norton current is just V3 over 6. All the other relationships are the same. Brandon. Fall 2020, 6 and 7. All right, so Thevenin voltage, positive polarity on the top left. So that would imply that negative polarity is on the bottom right. So this is our VTH. I'm going to do nodal. And I'm going to do nodal in the laziest way possible. I'm going to make B my ground so that if I can solve for the nodal voltage at node A with respect to ground, that's my Thevenin voltage, right? So this will be, let's call it C and D, and this will be our nodal voltage VA, right? So I have a voltage relationship equation that says VA minus VD is equal to 8.4 volts. Then I'm going to have a KCL equation at my supernode. So let me write those currents out. That's going to be this current plus this current. The reason why my 11 ohm resistor isn't showing up in this equation is because I would be adding this current and this current together, and they very obviously cancel each other out, so there's no need to even bother putting them in there. Okay. So my KCL equation is going to look like 2.1 amps plus VD over 7 is equal to 0. Now I have KCL at node C. Actually, I don't even need to do KCL at node C. I have enough information here to be done. Because I can solve this for VD, and I know VA minus VD is 8.4 volts, which would allow me to solve for VA with respect to ground. So technically speaking, I can stop my nodal here because I have enough information to solve what I need to. But just for completion's sake, I'd have negative 2.1 amps plus VC over 8 plus VC over 5 is equal to 0. Yep, seems legit. Those are the only two currents leaving my supernode. That seems legit. Voltage relationship. Yeah, solve that system. VA is VTH. Yes, sir. Supernodes occur whenever we have a voltage source. Any voltage source, we form a supernode between the two nodes that the voltage source touch. You're thinking about super meshes. Super meshes are only dealing with interior current sources. All right, so that's how we do the Thevenin analysis of this guy. Now let's do the Norton. So for my Norton analysis, I am going to put a short through here, and I believe I'm told reference direction is down and to the right. So here's I Norton. And to make this into a 3-mesh system, I'm going to do the crazy thing of combining the 8 and the 5 ohm resistors in parallel into a single equivalent resistance so that I can eliminate a mesh. So none of this matters. This is 8 in parallel with 5 now. So here's mesh current I1, I2, and I3. We can see right from the jump that I3 is 2.1 amps. Around mesh 1, we'll have negative 8.4 volts plus 11 ohms times I1 minus I2 is equal to 0. And then around mesh 2, we will have 11 ohms times I2 minus I1 plus 7 ohms I2 is equal to 0. Solve that system. Our Norton current is I2 minus I3. Yes, ma'am. I didn't think about it. They're definitely in parallel, but I'm having trouble wrapping my head around if I combine them, what are things going to look like? No, you don't have to at all. I just did it without combining them. I'm just trying to see if like what the impact combining them would have. Because I think that's an interesting point that Elizabeth is making, or I think she's making. I combine the 8 and the 5 to make it easier. Will combining the 11 and the 7 make it any easier? And the short answer is I'm not really sure, because my concern is if I put the 11 in parallel with the 7 up here, it looks like I1 is flowing through the 7 ohm resistor, and I know that it isn't. So I'm concerned about that. That's my biggest concern there. So it's all about how we wind up redrawing it to make it work out okay. So I would leave this guy alone. Just arbitrarily, I know that's a shitty explanation, but because it seems more confusing to combine those two, because it's directly impacting the Norton current, I wouldn't touch it. Yeah. No, so let me run through that really quickly, because that's actually probably an easier way to do it. So the suggestion was we short out this guy here and we observe I Norton. All right. So what Brandon, isn't it? Yes. So what Brandon suggested is effectively the 2.1 amps of current, it splits up and it flows through these two resistors before recombining. So I'm going to draw this as kind of a thick blue arrow to say that that's just those two currents that are recombined, and they're going to flow through that short circuit, form a loop. He also said by inspection effectively that the voltage drop across this 11 ohm resistor is 8.4 volts, and the voltage drop across the 7 ohm resistor has to also be 8.4 volts because they are very much in parallel. So we know the current that's flowing down through here. And then we also know the current that's flowing down through here. And so from that, we should be able to use Kirchhoff's current law and solve for I Norton without actually setting up a system of equations at all. So didn't even think about that, but yeah, you're 100% right. You're applying KCL, KVL, all that stuff correctly, so you shouldn't have any issues with it. Yes, ma'am. So, but you don't even need a table. If you have a calculator in front of you, you can develop it, because it's literally in one time constant, it's going to look like e to the minus 1, which is 36 and some change percent. In 2 time constants, it's going to be e to the minus 2, 3 time constants, e to the minus 3, et cetera, et cetera, et cetera, because that's literally how a time constant is defined, as the amount of time it takes for it to drop to the ratio of the final value over the initial value is e to the minus 1 in 1 time constant, e to the minus 2 in 2 time constant, et cetera, et cetera, et cetera. So as far as your test is concerned, though, 5 time constants is by definition the amount of time it takes for the signal to drop to less than 1%, which is the time that engineers have arbitrarily said means our capacitor is fully charged or fully discharged. So next. Yes, ma'am. Yes. So the test source method is used to find the equivalent resistance of a network. It can be done to find the equivalent resistance of any network, but we need to be looking at a dead network. This particular circuit only has a dependent source. It does not have any independent sources, so we literally can do nothing but apply the test source method. No other option works for us. So for this one, you want to use a voltage source or a current source? Voltage source. Let's just make it 1 volt for the sake of argument. And then our test current will be the current that's leaving the positive polarity terminal. And let's mesh it up. So I can see that 0.7 Vx is equal to I2 minus I1. I can also see that Vx is equal to -4 ohms times I1. And now I'm going to write a KVL equation around the outside. So that's going to be 2 plus 4 is going to look like 6 ohms I1 plus 9 ohms I2 plus 1 volt is equal to 0. And I can also observe that I test is just negative I2. And that should be enough information for us to solve for I test. Then our Thevenin resistance is just going to be 1 volt divided by I test. Sure. So for this problem up here, because it has a independent source, I could find the Thevenin voltage, find the Norton current, and then take the ratio of those two quantities, and that would give me my Thevenin resistance. Yep. Correct. Brandon. So let me erase all this junk. So here's my test current source. Just arbitrarily choosing 1 amp. Here's my voltage V test. Probably the easiest way to solve for this voltage would be nodal analysis, choosing that as ground. So let's call this V1, V2, and V3, where V3 is the same thing as V test. We could say that Vx is equal to V2 minus V1. And then we would have KCL at node 1. So that's going to look like V1 over 2 plus V1 minus V2 over 4 is equal to 0. KCL at V2 is going to look like V2 minus V1 over 4 minus 0.7 Vx plus V2 minus V3 over 9. KCL at node 3 is going to give us V3 minus V2 over 9 minus 1 amp is equal to 0. We can see that V test is equal to V3, and our Thevenin resistance is V test over 1 amp. So that's how I would solve it if I were doing a test current source. Entirely different circuit.
If it was a set.
If it was the same circuit, sure, yes. Mhm. It is a different circuit, right? Yeah, very much a different circuit. Okay. Next. All right, see you guys later.